Okay, so now we're going to hear Jacob King present his ICC presentation on CRC-Aided list decoding of convolutional and polar codes for short messages, specifically in 5G. Go ahead, Jacob.
All right, just to make sure you can see my screen, all good? All right, good. So good morning. I'll be presenting the paper that we've written that was accepted to ICC, the title, which is CRC-Aided list decoding of convolutional and polar codes for short messages in 5G. Before we start, I just want to quickly thank all of my co-authors, who you can see listed here. There we go. So I'll briefly start by introducing polar codes. In 2008, polar codes and the concept of channel polarization were first described by Arikon in his paper. And polar codes are notable for being the first code that have been shown to achieve channel capacity, which is an important milestone. With the amount of attention that polar codes have received in the 15-ish years since they've been introduced, they have found their way into the 5G standard. The physical broadcast channel uses a polar code concatenated with the CRC. While polar codes can achieve capacity at infinite block length, they perform worse and have some issues at the shorter block lengths used in the PBCH in 5G. And as such, there are multiple ways that we can improve on this PBCH polar code. So the contributions, we have two contributions to improve this specific 5G PBCH polar code. The first is by optimizing the CRC length of the polar code in order to lower the total failure rate of the code. And the second is by instead replacing the polar code with a tail-biting convolutional code concatenated with the CRC. We'll now go over the details of the polar and convolutional codes that we considered in this paper. Here we can see a block diagram of the polar code that is used in the PBCH. We start with a 32-bit message and append with a 24-bit CRC. This 56-bit CRC word is then polar encoded to 512 bits, and then repetition is applied to get a final code word of 864 bits. We analyze a number of alternative polar codes to this 5G polar code as well. All of our polar codes begin with a 32-bit message in order to fit with the PBCH. And all of them encode to an 864-bit code word. There are many different CRCs that we considered. The first one is the 24-bit CRC that is given in the 5G standard for the PBCH. We also use a shorter 11-bit CRC. This CRC is in the standard, but it's not used for the PBCH code. It's used for a different code. We also reached out to Sanka Baicheva and Peter Kazakov, who provided an 11-bit and a 12-bit CRC for us to use with our polar codes. Finally, the decoder we use is a successive cancellation list decoder. The successive cancellation decoder was introduced by Arikon in his paper, and it generalizes well to work with list decoding. For all of our TBCCs, we'll start with a 32-bit message as well. We use a rate 1/5 convolutional code with the generator polynomials that you can see here. We also use many CRC lengths varying between 8 and 16 bits, the CRC polynomials for all of which you can see here. And our decoder is the list-Viterbi algorithm decoder, which is a standard decoder for convolutional codes. Because varying the CRC length changes the code rate for these convolutional codes, and also all of these convolutional codes have a different code rate than the polar codes, we use EB over M naught as an SNR metric to compare against, which works well for comparing codes of different rates since it adjusts for code rate. So now we get to how we decide CRC selection. Why did we choose to use the CRCs we did? In 2015, blue described distance spectrum optimal CRCs for zero terminated convolutional codes, as well as efficient algorithms to find them. And then Yang generalized this to tail-binding convolutional codes in 2020. Distance spectrum optimal CRCs work by maximizing the minimum distance of the CRC code, which has been shown to be optimal. The DSO CRCs for the tail-binding convolutional codes were found through an exhaustive search of the CRCs in the space. The CRCs for the polar code are not designed for this specific polar code, however. They are not distance spectrum optimal. They are, however, CRCs that work well in general. Designing DSO CRCs for specific polar codes is an interesting area of future research. I'll briefly overview our list decoding scheme. We use a parallel list decoder with an exponentially increasing list size. The algorithm is as follows. We begin by initializing our list size L to 1. We then run our decoder with list size L. If it is a TVCC, we use the LVA decoder, otherwise we use the SEL decoder. We then check to see if any candidate code words on our list pass the CRC check. If one does, we select that as our code word. If not, we then check to see if our current list size is equivalent to our maximum list size. If our list size does equal our maximum list size and we still haven't found the code word that passes, we record an erasure and terminate. Otherwise, we double our list size and rerun our decoder. There are 3 possible outcomes for this decoder. If a code word passes the CRC check, it is either the correct code word or an undetected error. If no code word is found, then it is an erasure. And here we are interested in minimizing the total failure rate, which is the sum of the erasure rate and the undetected error rate. So now we can get to looking at some of our plots. Here we can see how we're optimizing the CRC length for the TVCC. All of these codes were simulated with a maximum list size of 2048. The solid lines at the top are at an EV over N naught of 2.5 dB, and the dashed lines below are at 3.5 dB. There are a couple trends that we can see on this plot of these different error curves. The first is that as CRC length increases, the erasure rate increases and the undetected error rate decreases. Longer CRCs add greater error detection capabilities, which makes undetected error code words much more rare and decreases this error rate. These two effects combined result in a total failure rate being minimized somewhere in the middle at a CRC length of 11 or 12 bits. We can see here that EV over N naught can change which CRC length minimizes this failure rate. However, even though there is variance in this, the nearby CRC lengths are very close. So we can see that the optimal CRC length is going to be somewhere in this range of 10 to 13 bits. Here, we can see some total failure rate curves for many of our codes. These have a constant maximum list size of 32. At the top here, we can see the 5G polar code with the 24-bit CRC, which performs noticeably worse than the other codes that we are comparing against. Here, at low values of EV over N naught, the polar codes with shorter CRCs and the convolutional codes all have similar performance, but at high values of EV over N naught, we see that the polar codes have a bit of a flooring behavior and start to taper off, where in contrast, the TVCCs do not have this flooring behavior and start to perform better than the polar codes at these high values of EV over N naught. A factor not shown on this plot is that the complexity of the decoders for each of these codes is actually not equivalent. So on this plot, we can compare the decoding runtimes and error performance of each code as the maximum list size varies. For this plot, all data points were taken at a constant value of EV over N naught at 3.5 dB. At the top here, we can see the 5G polar code with the 24-bit CRC, again, as we vary the list size. In the middle, we can see the polar codes with 11 and 12-bit CRCs, all of which have pretty comparable performance. And at the bottom, we can see our TBCC with an 11-bit CRC, which was the TBCC that performed the best overall of the different CRC lengths. There are a number of trends we can see here. The first is that is how maximum list size can affect both failure rate and decoding runtime. When the maximum list size is small, increasing the maximum list size provides a substantial decrease in failure rate with negligible impact on decoding runtime. However, once the maximum list size reaches a certain point, increasing it further has the opposite effect, with adding significant penalty to runtime with a very small impact on failure rate. We can also see that each code can support different maximum list sizes at equivalent runtimes. We can look at this series of points at around 2.4 milliseconds as an example. The 5G polar code can only support a maximum list size of 32 at this runtime and has a total failure rate of around 2 × 10⁻³ compared with the shorter CRCs on the polar codes. These codes can support up to a list size of 64, and the total failure rate gets reduced by a factor of around 100. Meanwhile, the convolutional code can support a list size as high as 1024 at this runtime and decreases the error rate by another factor of 10. We also show that this relationship between these codes is not limited specifically to an EB over N naught of 3.5 dB. This is a plot of those exact same codes with the same maximum list sizes in that slice on the previous slide, but we've run them over many different values of EB over N naught. And we can see a similar trend where the polar codes with shorter CRCs outperform the 5G polar code, and the tail-binding convolutional code performs even better than those. And we can even see a similar flooring behavior of the polar codes at high values of EB over N naught, while this is not exhibited by the convolutional code. This plot shows the performance of these codes compared to the RCU bound, which is an upper bound on the best possible performance of codes of finite block lengths presented by Polyansky in 2010. At the top, once again, is the 5G polar code, a full 2 dB away from the RCU bound for codes of its rate. The polar codes with shorter CRC perform better, but the error flooring causes the distance to RCU bound to increase at lower error rates. The convolutional codes here with a maximum list size of 32 perform even better, around 0.6 to 0.8 dB from RCU bound. And if we increase the list size to 2048, we can get that gap down to around 0.2 dB. As shown on our complexity plot earlier, we would not expect increasing the list size any further to have a significant reduction of this gapped RCU bound. Finally, we note that the polar codes are rate 32 over 864, and the convolutional codes have a significantly higher rate than this. The rates of the convolutional codes vary, but they are all around 4 times higher rate than the polar codes. For an equivalent comparison, we could take one of our convolutional codes and apply repetition to match the rate of the polar code. However, applying repetition, we would not expect to have any impact on error performance when comparing against EB over N naught. And just to confirm, we simulated this, and the plot on the right shows this. The repetition convolutional code has almost exactly the same error performance as the non-repetition with just minor variance. In conclusion, both shortening the CRC of the 5G PBCH polar code and replacing it with a tail-binding convolutional code can improve the performance of this PBCH code. Different decoders have different complexities, and this can result in different decoding runtimes and different maximum list sizes that they could support. Increasing the maximum list size can improve performance, but only up to a point. Eventually, we get negligible returns from increasing the list size further. And overall, the tail-binding convolutional code performs best out of the codes that we simulated in terms of both total failure rate and decoding runtime. That concludes my presentation. Thank you for watching. All right, questions, comments, or suggestions?
So I have a question regarding so code rate for 5G is like 1/27, right?
Yes.
And do you have any comparison with the 5G PBRL code for the same rate?
No, I have not compared to the PBRL code.
And also, I suggest you put slide number somewhere that if, audience have a question, they can refer to that slide number.
Okay, thank you. I will do that.
So I think that one of the, I have a couple of comments. One is that the DSO CRC, you said, let's go back to that slide where you talk about the DSO CRC way in the beginning. By the way, I love the way, great talk, and I love the way that you put a little red ring around the plot that I'm supposed to pay attention to. Sometimes I make people like introduce the curves one at a time, but I feel like what you did was even better. It was a really great way to help the audience follow along with a complicated plot.
Yeah, I knew that, well, I'm not going to go back to it, but I knew that that plot there was a lot going on there. And so I kind of needed to just go through each thing I wanted to talk about one at a time, make sure the attention was being drawn to the thing I wanted to talk about at a given time.
So this wasn't your, it's not the thing that you focused on, but we definitely want to get this right. It's a subtle point. So, so the distance spectrum optimal CRC wouldn't always be the one that maximizes the minimum distance. And so strictly speaking, like what Chung, if you read Chung Yu's paper carefully, what he was trying to say was, if I use the union bound, I can compute a frame error rate. And so if I have a distance spectrum, so I know, the number of neighbors at each distance, then I can use a union bound to compute the frame error rate. And I will pick the CRC because I'm going to check them all. I'll pick the CRC that gives me the distance spectrum that gives me the best frame error rate at the SNR that I care about. Okay, so that's why it's called distance spectrum optimal. Right. The minimum distance is like one part of the spectrum, but at the end of the day, you're right that at high SNR, all of that complicated analysis typically means that we want the CRC that maximizes the minimum distance. But I just want to, they're not the same thing. It's just in a specific case. So we should maybe take another sentence, and I'll put all this in the Slack. Now,
he also says of the CRC code.
Right, and it should be the concatenation of the CRC and the convolutional code.
Okay, thank you.
Yeah, so, yeah, and I'll have to edit thank you, Bill. I meant to say that too. Yeah, so that caught my attention. So it's not the CRC, it's the concatenation. So there's a lot to, and it's not like you want to focus on this, but I just don't want you to get into somebody picking on you like, well, wait, is that what it's unlikely because, besides Bill and me, I don't think anybody in the audience is going to be following that closely about the CRC design. That's our thing, but still, we want to be clear.
Yeah, I want to make sure that what I'm saying is correct. I don't want to say things that are wrong. So yeah. I appreciate all this.
So at the beginning, I'm sorry, I think we've talked about this before, and Bill, maybe you can correct me if I'm mistaken, but I think it's a strong claim to say that polar codes are the first code to be proven to achieve capacity. I thought that there were a few proofs or arguments about other codes. So, I mean, if it's true, I'm happy to go with it, but we don't need it for this talk. We can just say that, and they have been proven to achieve capacity asymptotically would be fine with me. What do you think, Bill?
Yeah, you're right. Since it's not really the focus of the talk, I would stay away from that sort of wording. But yeah, people do say, Rick, that they're the first class of codes that provably achieve capacity. But he can stay away from that just to be safe.
Because I thought there were proofs that read Muller codes achieve capacity, or maybe those proofs have come later.
It came later, yeah.
Or
Activity.
linear code families. I feel like even like 10 years ago, there were proofs about certain families of codes achieving capacity. But I guess maybe they were more like random arguments, or not quite as precise as you can do exactly this.
I think
Is that
that's
the
also a sentence in Ericson's original paper.
That he claims they're the first
Yeah,
codes.
yeah, yes. If you read the introduction, the sentence is there.
All right, then I don't see any reason. I mean, if it's true, it's true. It's just something that surprised me.
So I also had a question on this slide. So is that also the sentence you copy from the paper? But if that's the case, then we also need to change the sentence in the paper.
At the beginning, the introduction.
Maximizing the minimum
Oh, no, sorry.
of the CRC code that should be changed to the concatenated code.
No, I didn't copy that directly from the paper.
Okay, so in the paper, it's right.
Yeah, this
Okay.
is just, I guess, showing my ignorance on this topic.
So I have a list of quick comments. So you said the Ericon polar codes were published in 2008, and then down below you give the reference, which is 2009.
Oh, whoops.
And
Oh yeah, I mean it. When it appears on the IT transaction, it is 2009. The 2008 is the preprint version.
yeah, and then it's one of the bullets. I'm going to go quickly. One of the bullets you say optimizing the CRC, but later on it's CRC length. And so your bullet says optimizing the CRC, but really it's optimizing CRC length for that polar code. See, one of your images was blurry. The one that shows the encoding with the 32 bits in.
Oh, okay, I can make that.
And then
not
you
blurry.
didn't, I don't think you defined total failure rate. That's not as common as bit error rate or block error rate. So I think you should carefully define it.
Yeah, I do talk about it briefly right here, but I should make that more clear.
Okay.
As you get its own bullet point somewhere.
Yeah, okay. And then the last thing is, I agree with Rick. You did a great job encircling the curves that you were talking about, and you did it later. There was one where I said, okay, nobody knows what he's talking about, because you have a legend with 6 curves or 8 curves. And so there was one where you didn't do it, but I agree with Professor Wessel. You did a wonderful job. So one of the earlier curves, I would also do it there. There's 1 or 2 of them where you didn't do it. I think it was before this one.
This one, no, is it this one?
It might have been this one where it was just hard to. Yeah, I think it might have been this one. But
Okay. I'll more clearly.
Anyway, I just
circle,
remember
yeah.
thinking that the audience is going to look at that and say, okay, that's hard to sort out, because that legend is not helpful to the audience.
Right. Yeah. Yeah. This one I don't specifically circle the codes in this section. I call out like sections of them. But I will add circles.
Well, you know what you could do to make it even better, since you've gone to the trouble of adding those circles and you got the animation where you're bringing them in. If with each circle you have like a block of text saying, like let's go back in time to the beginning. Yeah, right there. So when you bring in that circle, you can have a box pointing to the circle and saying, this is the original 5G polar code with original CRC, and then when you go to the next one and you circle those guys, now that's a circle that's confusing. What are you saying for this circle?
So this one, I was trying to point out how the convolutional codes and the polar codes have similar performance at low EV over N naught. But I agree that I should add something in between these two, where I'm just circling the polar codes and saying these are the polar codes, and then.
And it'd be nice to point out that lowest curve on the right is your code, right? at some point.
Yeah.
The very lowest curve.
Yeah, that's a good idea.
Yeah, that might be a good, yeah, I think, but you could add word boxes to the circles.
Mhm.
So, and kind of go slowly as you
Okay.
bring these things in.
Yeah.
So, yeah, and you might think about the legend. Like,
Mhm.
what does the person need? The acronyms are not working for this. So for this talk, you know,
We don't need the legend.
well, no, you probably need a legend.
It might
But you
help
need a legend
you.
that has, like, you don't need the LMAX 32, they all have that.
Mhm.
And the rates may not be that important. They're
Mhm.
all different, and the user's not going to follow that, but you're using EV over and zero, and you already told us the rates are different. So it might be like spelling out, this is tail biting convolutional code, this is a polar code using words instead of acronyms, and the CRC size. I think that's it. The coding style and the CRC size are the things that matter in this plot. And so you could make a simpler legend and then, or not have a legend and instead have word boxes grouping the curves. You know, I don't know. Yeah. So, but I think what Bill is saying is try harder for this slide to make it clear.
And PC is not that helpful. I'd rather have you spell out polar.
Yeah. You could use the word polar or polar code. Yeah.
Yeah.
So probably
all.
no acronyms on the slide, and think about how you're going to identify every curve in a way that in the way the reader cares about, and don't bother saying things that the reader, that your audience is never going to take in anyway. You know, like the 32 over 215 versus 32 over 220. That's for somebody reading the paper, not for somebody watching the talk.
Right.
I think another comment on this slide is instead of trying to copy the caption here, you can just type it so that the fonts are much more clearer.
Oh yeah, nobody's going to read that caption quite that way, but that's fine. You know, that's the first iteration. Now we can have a second. In fact, really, to fully think about that white space on the right-hand side as a huge resource that you are not using.
Right.
And so you could have you could keep this, you bring in and circle a plot, you can have an arrow connecting it to a text box over on the right. And by the end of the plot, you've got all of the text boxes are still there, identifying all the curves. You're sort of bringing in the legend one item at a time. You know, I don't know. You can do these are some ideas.
Yeah, that's an interesting suggestion. I'll play around with it, see what I like the most.
So I think I think Bill might have other comments.
Actually, that was my last one. Thank you.
I still have one more thing I'd like to bring up. And so let's go back to where you figured out the right CRC length. Okay, so, you know, this is something that we kind of didn't pay attention to, and it's fine. We picked our metric total failure rate, and we're allowed to do that. But it could be that the people who designed the 5G standard cared also about the yellow curve itself, the undetected error rate, and were unwilling to have an undetected error rate higher than, say, 10 to the minus 10 or something. Hence the 24-bit CRC. In other words, they were less concerned about losing a packet than actually having a packet that's wrong and not knowing it. And so in your talk, just to avoid someone, you know, bringing it up and then you finding yourself on your back foot, I think in the talk, and I don't know if there's still time to change anything. I think we can still make a change to the paper, right? I feel like just a sentence saying, okay, you might be interested in a lower undetected error rate, in which case you would use a longer CRC, is not a bad, it's not a bad idea for us to recognize this issue. Like we're picking the lowest total failure rate, but that happens to be at certainly not the lowest undetected error rate. The undetected error rate keeps going down as you increase the CRC size. And I think Bill and I think, share the opinion that if one wants to have a very low undetected error rate, actually the better way to do that would be after you've got a great channel code, you add another CRC whose only purpose is to avoid a mistake. And that design that CRC to be long enough to avoid that undetected error. But it actually wouldn't, I think at the end of the day, my guess is it doesn't matter whether you design a separate CRC or just include it by making this CRC longer. You're going to lose some rate, but you get something in return, which is this lower undetected error rate. But I just think you don't want to just not talk about it, because it's fair for someone to have a different criterion, and it may well be that the 5G committee had a different criterion, in which case our work, while it's informative about how to have a better total failure rate, it may not mean that the standard would immediately jump on our approach. What do you think about that, Bill?
Yeah, there are two reasons. That might be the only question he gets, because one of our reviewers brought that up. Oh, wait a minute, and they had some design criterion, and you guys are kind of ignoring the detection error rate probability. Undetected error probability. And so, yeah, so Jacob should think about it for number one, and number two, we should try to fit at least a sentence in the paper if there's room. Yeah, I agree with what you said, but, Jacob should be prepared, because, that's at the forefront of my mind. Like, people are going to go, oh, that's not really fair. You have a different criterion than maybe the 5G guys did.
Yeah. And that's where, and I added in the Slack, probably we should think about, like, what would our answer be if we said to ourselves, well, we want the highest rate that we can get, but we need to have an undetected error rate of 10 to the minus 10. Where would that leave us? What would our answer be? And it might be, if you sort of follow that plot down. It also depends on what SNR we're talking about, but I wonder actually if you could, with a 24-bit CRC, I suppose they have an undetected error rate of 10 to the minus 10, even when the thing isn't working. Like, that's different from erasure rate.
But what's good about the techniques you guys have developed, like the two papers that he cited, Liu et al. and the other paper, is you use that to design the CRC, and then use it again to design the other CRC for error detection that you talked about. Right. It's the same criterion. And so he can say that, like, we can use these same techniques to design an outer CRC that's used just for detection.
Oh, I like that. That's a great way of making it sound like, we're not giving anything up.
Yeah.
But yeah. So, but I think that, like, and I guess I'm saying in the journal paper, we might want to go ahead and do that if we can. It may not be so easy because, well, I don't know. That's actually an open research problem. Like, well, what's harder, designing one CRC that accomplishes both things, or designing the second CRC on top of this system, which I do think is somehow conceptually, I feel like they're separate problems and should be treated separately. Do you feel that way too, Bill?
I do too. Yeah, I think it requires some thought.
But I think that, but I also think that our CRC design techniques might actually be stretched to find this outer CRC, because it's operating on a pretty long. I guess Hung Jae would be the expert here. What do you think, Hung Jae? If we already have a system that's, what is our blue curve? What is that, Jacob? That code is V equals what? M equals what?
Sorry, which curve?
The one that I said was the lowest curve.
I think it's M equals 11.
On this plot, you mean?
Yeah, the
okay.
blue curve. What's V? Well, how big is the convolutional code?
I believe it was 8 memory elements.
I think so too.
I don't actually say that in here.
I think
we should add that in the talk. You should talk about the complexity.
Yeah, it's 8 memory elements. I can put that in.
Good. Hung Jae, can we design an outer CRC if we already have V equals 11 or V equals 8, M equals 11? Now I want to add another CRC.
Let me think. I think it should be doable. I mean, when you are searching for the optimal CRC, then of course, at the same time, you know the set of undetected errors, and maybe you can try to reuse them to design another CRC.
Yeah.
Yes. So we've actually, by the time you found the optimal CRC, you're sitting on top of the mistakes that you haven't been able to get rid of.
Right.
And we could collect up. It's really a question of collecting up all of those mistakes and saying, how do I get rid of these mistakes?
As you can imagine, it's going to be like a nested process. So you keep reusing the previous undetected errors to get a better CRC. And what you are describing right now is like you are thinking of the CRC polynomial as a product of two smaller CRC polynomials, right?
Yeah.
Yeah. And I think in the past, we also did some research on this question. The question is whether the optimal CRC is always decomposable to it can always be decomposed into multiple smaller CRCs. And I think most of the time the answer is yes. It is always can be decomposed into smaller CRC polynomials.
I feel like we also would want to do this design. I'm wondering whether it actually has to do with not just how it performs like at an operating SNR, but even in a very noisy channel, you still would want not to make a mistake. Which actually means that you would want the CRC naturally to have a lot of because we might need 2 to the minus M to be based on our other work, you would need a CRC where 2 to the minus M is 10 to the minus 10. Do you know what I'm saying?
Mm-hmm.
Like even in that random environment, or maybe we don't need that. I mean, I guess we need to think about what is exactly our constraint. Like how noisy do we need to be? Do we need to have to make sure that we wouldn't make any errors?
Yes.
Okay.
You are talking about undetected errors, right? You are ignoring the erasure.
Right. I don't care about erasures. I care about undetected errors in this analysis. Because we'll have already gotten the performance that we want in terms of total failure rate.
Yeah, the total failure rate at low SNR is just close to 1.
Right. So is that where the 24, I think it's interesting to think about. Is that where the 24 comes from? That 2 to the minus 24 is 10 to the minus 10? I mean, they might have just done that way. Let's see here, 2. X to the Y.
That's not,
24.
yeah. It's not that low.
Yeah, that's only, I guess I don't have it in, that's how many zeros is that? That's 10 to the minus 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's even 24 bits, even if you do everything right, in a really noisy channel is only going to get you undetected error rate of about 5 times 10 to the minus 8. So,
okay, so people use 16-bit CRCs in practice. And so maybe your 10 to the minus 10 is you're being too hard on yourself, right?
yeah, exactly. Yeah,
Yeah.
so I just don't know. We just need to, what we need to do is we need to figure out from the 5G people, what is the, what was the spec?
Yeah.
Because if it is an undetected error rate of, it could still be 10 to the minus 10 as long as it's 10 to the minus 10 at 4 dB. You know, if it's 10 to the minus 10 at EB over N0 4 dB, we can get that no problem, you know, because we just have to clean out a few neighbors and be done with it. But if you're
Right.
saying, oh, and we also might run it on a ridiculously noisy channel and we want it not to accidentally decode, that's much harder. And our techniques wouldn't be as beneficial. Because you know, if the channel is noisy enough, there's nothing you can do except for have a very long CRC because it's just random at that point.
Right.
So anyway, I guess, yeah, I think the thing to do would be to just assume that people, because I think actually it's not a reasonable requirement, you know, just say, well, you have to work on a channel that has, you know, it's all noise and nothing, because that's not real. And we could just plot, like have a separate plot, which is plotting the undetected error rate alone. But you would see that even in those, if you go back to that other curve, where you were finding the minimum, yeah, you can see that it's going to have to be longer than even at, let's say we only care about 3.5 dB, we're going to have to go out another, you know, if you sort of extend that line, we're going to have to go out a few more bits to get to 10 to the minus 8 even, you know. I might be able to see 10 to the minus 8 happening with a 24-bit CRC, you know. I don't know, it may go down faster, but it's something we might want to look at. Okay, I'll stop talking about it. Anything else people would like to talk about?
I
Yeah.
also have a question on this slide. So the first question is, I noticed that if you increase the CRC length, then the total failure rate gets higher. Can you offer an explanation or intuition about why do we observe this phenomenon? And the second question on this plot is, so your title is optimizing CRC length for the TVCC, but look, it seems to me that you can only do this by simulating a range of CRC lengths so that you can know where is your optimal spot, right? Is that what you do in practice, that you need to estimate a range of CRC bits you might be interested in and then simulate each one and get this plot to determine your optimal CRC length? That's my two questions.
I'll answer the second one first. That is what we did in practice. I'm sure there are more maybe mathematically rigorous ways that we could approach this. But in this paper, we just picked on a range that we thought would be good and simulated these points and picked which ones seemed optimal for this.
I see. So in that sense, it looks like it still requires much more complexity to identify this optimal CRC length, right?
Yes.
Okay.
Yes. As for as for why the failure rate gets higher as the number of CRC bits increases, this is because this is at a constant value of EB over N naught, which adjusts for code rate. And as we increase the length of the CRC, this decreases the rate of the convolutional code, which has if we compare at equivalent values of EB over N naught, this results in a higher noise level for the codes with longer CRC lengths. So that is why the error length increases, because the noise level is actually getting higher to adjust for the lower code rate.
Okay.
And another way to, and why is it that we're lowering the rate but not able to work on the noisier channel that we would have expected we would work on? There's another mechanism here, Jacob, that you might want to talk about. Mm-hmm. And so where are we getting the longer CRC bits? Oh no, that's only for the polar code.
Yes.
Yeah.
For the polar code, I'll just go on this slide. The polar code also has a longer CRC, having a worse error performance. But the polar code doesn't have this rate issue. All of the polar codes are rate 32 over 864. This effect comes from longer CRCs mean there are fewer bits that are frozen. and therefore there are more bits into which errors can be introduced. By having a shorter CRC, there are more frozen bits, and so we're using more reliable channels, basically, or with the another way to think about it is with the longer CRC, we are using some channels that are less reliable, that in the shorter CRCs, we are freezing them.
Yeah.
I still have a question about the previous plot. So I'm thinking at a fixed SNR value, if your rate gets lower, shouldn't your FER also get lower? Why you say it will be higher?
Because it's not fixed signal to noise ratio, it's fixed EB over N naught, so energy per information bit. Okay, and so if you increase the CRC size, you lower the rate. And so for a given number of transmitted symbols, you have fewer information bits and therefore smaller total energy. And so your transmitted symbols have less energy. And so they're just not, it's not going to work as well. I mean, the extra CRC could come in and help you to deal with that lower signal level, but it turns out it doesn't help enough.
Okay, so you are saying we need to think about this problem in terms of ES over naught?
If you plotted it versus ES over N naught, adding a longer CRC will only help you, can't make it worse.
Right.
Okay. So you're in that case, your failure rate will go down as you increase the CRC. And I can, if I increase the CRC to be, it'll never get worse. It might flatten out and stop helping, but it'll never get worse. But when it's EB over N0, when I increase the CRC size, rate goes down. That means the energy per symbol has to go down.
Okay, I see. Yeah.
So we could, that's something we could do. I know, there are all these, you can do anything, but we could make separate plots that plot, as you increase the CRC and keep the signal level the same, what's the total failure rate at a fixed ES over N0. And I imagine that what happens is it goes down, but then flattens out. Because there's a certain point at which you're no longer making erasures. The erasure rate goes to, or it goes low enough that it just doesn't matter. And so the only errors that you're making are erasures. And the erasure rate, after you've caught the erasure, making the CRC longer doesn't change the erasure. You've erased it. You don't need to know another bit that tells you it's not right. So I think what happens is if you plot it versus ES over N0, we might want to make one plot like this, Jacob, just so that we're confident, but what happens to the total failure rate is that it just goes flat. What happens to the erasure rate is that it goes flat. And what happens to the undetected error rate is it just keeps going down. It was your probability of undetected error was 10 to the minus 8. You make the CRC longer. Now it's 10 to the minus 9, but it's in the noise. It's not significant in terms of the total failure rate because it's so much smaller than the erasure rate that it doesn't affect the total failure rate. So then when you switch to EB over N0, that flat curve then has to be tilted up to account for the loss of signal level. That's pretty much the whole story.
Jacob, did you say when you presented this slide that blue curve was the sum of the other two curves?
No, I didn't say that.
Yeah, you might want to emphasize.
Good idea.
You could even put that in the legend. And again, you can have the, TFR equals, and again, acronyms aren't great for the slide. Remember that the way you're plotting it here, you've got a lot of white space around the slide that you could explain things.
All right. Yeah, I will fix that.
And for this plot, are you using the PNG format or the PDF? It looks a little bit blurry.
It does.
Oh, yeah. I think, the other ones are much clearer. I think I just made I probably just used the wrong file on this one. I can make that much clearer.
Okay, yeah. And
whatever you did for the other plots, do it for this one.
Yeah.
Yeah, I also have an additional comment. What does Oh, it's not a comment, it's a question. What does B and K CRC mean in your legend? I think it's a
Oh, yeah, okay, some
lot
more,
in the
there,
yeah,
here, yeah.
like this one.
Yeah,
Ah.
so this is, yeah, just another case of I should make the legends better. B and K is for Bycheva and Kazakov, who are the two who provided those CRCs for us.
Oh, okay, got it.
Yeah, just got to fix the legend.
Jacob, I have a question here. You compare tail biting convolutional code with the polar codes, but the rate of your tail biting codes are like a 4 times higher than the rate of the, I mean, TBC is higher by 4 times than the polar code. Is it possible to reduce the rate of the convolutional code in order to even get better performance for tail biting?
So I do something like that at the end where I apply repetition, and now as we expect repetition, but you're talking about just a different convolutional code
Yes,
that's at a lower rate.
Yes.
We probably could.
The answer is yes. What we did is we took one of Rick's and Hong Jae's codes, which I think was rate 1/5, and this just used it rather than ask them to design an even lower rate. But that's a good question, Dariush. Right, Rick. We can. You guys, Hong Jae could design an even lower rate than the 1/5.
Yeah, but then that will be much fair comparison of tail biting code, because the code rate here for tail biting is 4 times higher.
Yeah.
Maybe, but I got to tell you that for these very low, once the rate gets low enough, there's not much more to get. You're kidding yourself. It turns out the convolutional code you design ends up almost doing repetition. I don't really.
I believe if the constraint length is low, then yes, it becomes like repetition.
I mean, I guess I know we did a paper like that. Maybe it was turbo codes, but I've done something like that like 10 years ago, and we found out that at some point it's time to start repeating. So we could do even better, but our performance is close enough to the RCU bound that it seemed like maybe we're okay. That we don't. But you're right. We haven't totally nailed it down that there's not some benefit. I have to dig up those papers again about the super low rate.
And Jacob, you had another figure that shows dashed plot at the end, but you haven't specified what that dash plots. Yeah, these are what? These are lower bounds, or what are these?
Sorry, yeah. I should make the legend
Large
better
list.
once again. Yes, this is a very large list size. These are the same convolutional codes, but at a list size of 2048, whereas these are the list size of 32.
Oh, I see. So maybe you put, legend for that.
Yes.
I guess that's in the caption. Yeah. Or do you solid lines, dashed lines have Lmax equals 2048? Okay. So we just did that because we were running out of legend space. But for this talk, you need to, it's huge.
Yes, will do.
Yeah, make it crystal clear, and you can get rid of that caption.
Yeah.
Wait, do you have a comparison of any of the codes to RCU to get back to Dariush's first question? Like it's just that's what this is. Let's see.
Yes.
So which RCU though? Because we have different rates.
That's why it's plotted. That's
gap.
That's why this is such a clever way to do it.
I see. The relevant RCU. I see.
Yeah. Each curve has its own RCU bound. We're just plotting the distance. So this hides a lot of complexity.
But then to be fair, though, I'd like to see the distance between the rate 127 RCU. I'm just imitating what Dario said, and then the rate, whatever his is, 4/27, let's say.
That's a great way of understanding, like, what were we leaving on the table? Like,
Yeah.
how far, but we know already that those RCU bounds. So when you go from rate, since when we are within 0.2 dB with our rate 1/5 code of the RCU bound for the, oh, maybe not. You're saying we should compare everybody to the lowest rate RCU bound.
Well, this is great right here, but yeah, but at some point it would be nice to the lowest rate one, like, which is just what Dario said, basically. Like, you know, what can we gain? Is there anything else to gain, at least in theory?
Right.
So I think the way to handle that, Jacob, is to go back to for us, I don't know what we're going to present, and this is something we can think about for the journal paper, but, and it's a kind of a messy plot, but I think the thing to do is to start by plotting all the RCU bounds, which you must have because you had to have them to create this plot.
Yes, I have them.
Plot those RCU bounds versus EB over N0 for all the rates, okay? And then we can look at the differences to see if there's something that we are.
Yeah, if there's potential to, like what Darius was thinking about, is there a potential gain by going to even lower TBCC?
Yeah.
Yeah.
Because the RCU bound goes, that's something I guess that is hidden by this curve because we're comparing really to a higher rate RCU bound for this dashed curve, for all the non-green curves.
And in effect, we do have large memory, right? Because we have V = 8 and M = 11. And so it seems like it won't be repetition, maybe if we keep going to a lower rate. I don't know.
No, actually, to be honest, the M = 11 is giving us lower rate and doing it in a way that's not repetition and is clever. The CRC does it, you know?
That's right. Yeah.
So it's if we wanted to go lower rate, we could add more CRC bits, but we already know that's not going to help us. Yeah, that's interesting. Okay, so fine. It's something we could try. We could go to 1/10. We have to get the right 1/10 code and then to redesign the CRC and see what the difference is. It is something we need to do.
At least look at, yeah.
Yeah. The never-ending story.
Yeah.
What's the constraint length of convolutional code right now?
I think it was
E = 8.
M
Yeah.
= 8, memory 8.
Yes.
Memory 8, I see. So we should see that how many combination we can generate that does not create a repetition to see what's the lowest rate that we can design these codes.
Yeah.
Well, I mean, I think it's not that hard, right? There must be already in the literature, what's the best V = 8 rate 1/10 code, right?
Maybe.
I don't know if it exists or not.
Yeah, that's pretty low.
Okay, well, we can look into it. I guess, yeah, that is something we can explore. Okay, so I think that the two new action items here are, we need to plot RCU bounds versus RCU bounds versus EB over N0 for all the curves on the distance to RCU bound plot. Just as a way of seeing, like, what is because the RCU, what you're saying is the RCU bound for the polar code with the lowest rate actually should be the furthest to the left.
Yeah.
Even though that code is the worst performing code. So sort of two things are happening. It makes the polar code look even worse because it's not a great code, but it's at such a low rate that it should have a higher bound. So then the second thing is, okay, can we do better by starting with a lower rate convolutional code? And I guess we decided, well, let's see if we can do well with 1/5, and we just became self-satisfied that, oh, this is good. This is good enough.
That's right.
But it doesn't really answer the question, like, could we do better? And if we understood where the RCU bound was for the Super 8 code, it gives us a sense of how much better we might be able to do if we think that the RCU bound is sort of the limit. Although I have to say that Lin Fong has plots where we actually, for the coded modulation system, not this BPSK model, but a model where we're sending constellation points over short block lengths, where we actually cut through the RCU bound, and that's no longer, we're past it far enough that we have to start thinking about, well, what was the converse? What's the total limit on where we could be? So, and that's another thing to think about, that maybe, we really shouldn't be thinking about this RCU bound as our limit anyway. And we need to plot the meta converse or whatever, so that we see, like, well, somewhere in this band is where we want to be, and we're at least coming to the RCU bound. But in the earlier works for BPSK, we've never been able to really push. It's almost like you can see the curves start piling up as we get close to RCU. Anyway,
Yeah.
All right. I think we've gone past the hour. I appreciate everybody hanging in there. And I obviously it was the right choice not to have 2 talks. So, so we had your time was good in terms of 15 minutes, but we had a lot to talk about. I think it's been very fun. Thank you for your talk, Jacob. And I'll see everybody next week, where we're going to have Beryl presenting about high rate list codes. So thanks a lot, everybody. I'm going to stop the recording now. Thank you, Jacob. Excellent talk.
Yeah, thank you everyone for your suggestions and comments, everything. I appreciate it all.
Oh, I'm
You're
gonna-
welcome.